Hello, Dean Waldo here for a quick mini screencast on a concept that seems to cause a lot of confusion for students using Raman scattering. So what we're going to do is look at the wavelengths related to Stokes Raman scattering specifically. So very brief overview. Light comes into a system. It'll cause an electron in the ground state to go up to an excited state we call a virtual state, polarizing the electrons in its cloud or orbital. When that energy of the electron comes back to the ground state or comes back out, it may come back to the same place. We call that Rayleigh scattering, sometimes Mie scattering or Tyndall scattering. But if the energy of the electron comes down to a different level, so if it starts at the ground state, ends up at the first vibrational state, and the energy of the photon coming out is less, we call that Stokes energy. If the opposite occurs, we call it anti-Stokes, but for this example, we'll just look at Stokes. So to do that, in the text we're using, if you look at equations 12.1 and 12.2, those are what we're going to be focused on. So let's take an example. Let's suppose we have a carbon-carbon double bond that has a 1600 wave number vibration. And we have a lambda 0. The laser we're going to use is 1064 nanometers. Let's calculate the wavelength of light we expect to come out from a Raman-Stokes line where the electron comes back down to an excited vibrational level for a double bond vibration. So here is our lambda wavelength. Let's just calculate what the wave number of that excitation beam is. So that is going to be nu bar naught, and that's going to be 1/1064 nanometers times, there are 10 to the 7th nanometers per centimeter, and out of that we get 9,398.5 wave numbers. Now that is the energy and wave numbers of the laser exciting from the ground state to the virtual state. Now what we really want is, so that'll be nu bar naught, what we want is nu bar 1, the wave numbers. We want to think about what the wave numbers of the photon leaving the system is, and that's what we're going to see in Raman scattering. So we know in this case that the difference between nu1 and nu naught will be 1600 wave numbers. So in other words, if we say delta nu bar in units of wave numbers, we know that's going to be 1600 wave numbers. And if we calculate that as the incoming wave number minus the outgoing wave number, we know that should be 1600 in our case. But we actually want the wavelength of the outgoing photon. So let's convert things to wavelength. So that would be equivalent to 1/lambda 0 minus 1/lambda 1. And if we convert those into wave numbers from nanometers, we're going to have 10 to the 7th nanometers per centimeter. So if we look at this equation here, we know that this is going to be delta nu, and so this is essentially equation 12 from our book, 12.1 I should say. But if we want the wavelength, let's solve for lambda 1, and solving for lambda 1, we are going to get an expression that is lambda 1 is going to equal 1 divided by 1/lambda 0 minus parenthesis delta nu, and delta nu will be in wave numbers, so we have to convert wave numbers to nanometers, and we know that 1 centimeter is 10 to the 7th nanometers. And so if we plug in our values for this particular example, lambda 1 is going to equal 1/106 Let's try that again. We're going to have 1 divided by 1064 nanometers minus 1600 wave numbers, which is that vibrational frequency for the double bond. And we're going to convert that to inverse nanometers. That'll be 1 centimeter to cancel, divided by 10 to the 7th nanometers. That will give us a new wavelength that is about 1282.3 nanometers. So that is the wavelength of the photon leaving, and so let's just see what the wave, or the wave number for that would be. So that's just going to be 1 over 1282.3 nanometers. Converting that to inverse centimeters, or wave numbers, is going to be 7,798.5 wave numbers. So the difference, and I emphasize the difference between those two, should be our 1600 wave number vibration, because that's the energy that gets put into that vibrational excitation. So let's just double check. We know the new zero was 9,398.5 wave numbers, and we just calculated 7,798.5 wave numbers, and that turns out to be a difference of 1600 wave numbers. So I hope that helps clarify working with Raman scattering in terms of wavelengths and wave numbers. It's a good review of wave numbers as well. If you're interested, anti-Stokes is where you start up at one higher vibrational level and go down in the exciting photon. So instead of having the energy of the photon go down, the energy of the photon gets added to from the energy of the vibration. So the minus sign would be added to the 1600 wave numbers. Okay, and that's why wavelength for the Stokes shows up to the right, and wavelength for the anti-Stokes shows up at lower. So this is blue, and this is red in direction. Thank you.